Yeah, thank you, Sanyo. So I am Sandy Kambampati. I'm a principal research scientist here at Intact.Solutions. Um, so, so the outline of the talk, try to break it into three parts. The first thing is we at Intact Solutions, we have a simulation platform called Intact.Simulation, and it has a unique mesh-free environment where you can bring in different solvers. And I'll be talking about, how we plan to bring in MFEM into our ecosystem and how our framework leads to a decoupled design and simulation framework, which can be very useful for generative design applications. And finally, I'll be talking about how some of the commercial deployment of these applications. So just the background of the company. The company has been there for a while. It's a spin-off from University of Wisconsin-Madison. It's been there for a while. I joined the company in 2020. My background is in design and optimization from aerospace engineering. Aerospace engineering. Um, so here we have an immersed method of moments technology, which is essentially a mesh-free technology. What it means is users can simulate directly on native geometry and material models without any pre-processing, meshing, or any format conversion. That's the whole idea. What it means is users can bring in different kinds of geometry, implicits, B-reps, meshes, G-codes, CT scan data, voxel data, and they can mix and match all these different geometries to set up simulations. And here we have kind of four different aspects that we do. So first is the SDK. So we have a C++ API available on Windows and Linux of our software. We have integrations with other CAD providers. We have integrations with NTOP, Onshape, Cinera, and even Rhino. More recently, we started developing a Python package called PyIntact, which runs essentially in headless mode, and our users are using it to set up machine learning applications. But last but not least, most of our funding is from advanced R&D projects. So we are primarily funded by DARPA. We got funding from NASA, NEST, NSF, ONR, and currently we are getting funding from the Department of Energy to kind of utilize MFEM to bring MFEM into our ecosystem to do generative design and optimization applications for additive parts. So that's the big picture of what we do here at Intact. All right, so here I'm just going to give a high overview of the fundamentals of what we do. So like we always say this, meshes are great. Everyone likes meshes. There are different kinds of meshes, pretty cool. It's not the meshes, it's the meshing is the problem. Everyone knows it's a headache. There's several things, right? You need to look at the quality of the mesh, the ratios, the aspect ratios. And before you can do meshing, you need to clean up your geometry. You need to defeature it. If there are any naked edges, you need to take them out. It's a lot of work. Everyone hates meshing. Everyone loves meshes, right? So what at Intact? So we developed this simulation platform called Intact.Simulation. It's something it's immersed grid methodology to eliminate meshing. So I think some of you guys may be aware of the immersed grid idea, but essentially in this picture, so on the left you have some geometry, right? This is a brake pedal example, and it's native geometry. It can be in any format. It can be a CAD, STL, G-code, voxels, scan data. It doesn't matter as long as the geometry has a proper definition. It doesn't matter. All you need to do is take that geometry and immerse it in a background grid. So here in this case, the background grid is hexahedral elements. And construction of this background grid, especially if it's a structured grid, it's embarrassingly trivial. And you can control the resolution of the background grid at runtime if you want, but that's an essentially automated process. There's nothing fancy going on there. Now, once you have this background grid, you need to solve two problems. One is you have to enforce boundary conditions. So if there are loads applied, if there are Dirichlet boundary conditions, etc., you want to apply them on the FEA grid, right? So that's one challenge. And the second challenge is obviously you need to compute stiffness matrices, mass matrices, which means you need some kind of an integration routine going on. So in our company, we developed this thing called as the moment vector technology that can compute quadrature at one time. I'll be talking about that. And so we have these two challenges, and once you overcome these challenges, you can solve it on the background grid and project the solution back on the native geometry. So essentially what we are trying to do is we are trying to eliminate meshing by replacing meshing with this automated, background grid generation. So that's the idea. We have papers on what we do. We publish them. Happy to send them. Happy to send you a copy if you request it. So the first challenge is about boundary conditions, right? So if you have a conventional mesh, well, you can apply boundary conditions directly on mesh nodes. It's not that difficult, right? You just select the nodes, say displacement is 0, flux is so and so, force is so and so, and you're done, right? But in immersed methods, there may not be any nodes on the boundary, and that's obviously a problem, right? So there are two ways of solving this. So there's an old method called as the Kantorovich method. Hopefully, I didn't screw up the name. It's a really old method, 1950s. It started off in the 1950s, and people have slowly developed the technology, and now there are a handful of software that use this. So the idea is this. So let's say you have a simple Poisson equation, del square u equal to -2, and then you have a Dirichlet boundary condition, let's say u on some boundary 0, and the boundary is this cut of a circle, right? So the idea here is the solution u, you express the solution of product of two functions, omega and phi. And then you choose omega that automatically satisfies these boundary conditions. So for example, if you choose an omega like this, right? That means if u is expressed as omega times phi, u automatically satisfies this Dirichlet boundary condition, right? No matter what phi is. And then what you need to do is you need to express phi as standard linear combination of basis functions, standard FEA basis functions. And then the procedure is simple. Construct your weak form, minimize the weak form, find the coefficients that minimize the weak form, and then everything is basically standard FEA. So this is what we are calling a strong implementation, but there's a catch here. So you're multiplying two functions here, right? So let's say your basis function is quadratic. Now you're multiplying quadratic with omega. Let's say if omega is also quadratic. So now you're multiplying quadratic with quadratic, which means now your functions are fourth order polynomial, which means your quadrature should be much better, much higher than typical quadrature. So the requirement on the quadrature can cause errors, and that's a problem. It's a very elegant method, but there can be implementation challenges. Now, there's an alternate set of methods. Let's call it as a weak implementation. So in weak implementation, what people do is they penalize any deviation from this boundary condition. So they take this boundary condition and any deviations about it, they penalize it with let's call beta as the penalty parameter. There are different methods for weak implementation. So if you have a standard penalty method, you would have highly ill-conditioned stiffness matrices, and that creates problems. Niche's method is an alternative method. It's a stabilized method, so which means you don't really need high values of this penalty parameter. So this is weak implementation, and in our platform, the users can choose strong implementation or weak implementation. But essentially, what I'm trying to say is we have this challenge covered about specifically the challenge about boundary conditions. We have methods to solve this. So the consequence of having the strong and weak implementation is that it offers a way to interoperate with other FEA solvers. Now, what I mean is this. So this is a heat sink part, and we wanted to do simulation on this, but we wanted to use MFEM. So we chose to do the strong implementation, which means that the code base, the FEA engine must be open source. So luckily for us, MFEM is open source. So we could go into MFEM and we overloaded the shape functions. We multiplied that by omega that I described in the previous slide. And we were able to set up a simulation going, and this is the simulation result. It shows the temperature distribution. So with MFEM, we implemented the strong implementation way, which needed overriding shape functions. Now we have some users who don't really want to change their solvers, so they've been using Nastran for like 10, 15 years. They're happy with Nastran, and Nastran is required in aerospace and defense applications, so they don't want to touch it. They don't want to, mess with the source code. And Nastran is written in Fortran. I don't understand Fortran. Never learned it. I don't want to mess with Fortran. So in some cases, you don't want to mess with the source code, right? So in that cases, the weak implementation can come in very handy. So in this case, what we did is we took this part. As you can see, it has many, many tiny features. It's a nightmare to mesh. So what we did is we created essentially an equivalent model. So we took this geometry, immersed it in a background grid, and then we created an equivalent model that Nastran can understand. Nastran solves it, it sends out the solution. We take the solution back and project it back on the native geometry. So what I wanted to communicate here is that we have two ways of doing this. We can work with open source solvers. We can work with closed source solvers like Nastran. And we have this cool interoperable FEA platform. The other challenge that I described is about integration. So let me try to explain this integration using this picture. So let's say you have a simple geometry here, right? And we are immersing this background grid. So here the background grid is shown in blue here. So what we do is we collect these integrals of polynomials. So here it's a simple first order combination of polynomials, 1, x, y, and xy. So what we do is we take this geometry and then we multiply these shape functions, 1x, y, xy, and then we integrate over geometry. Now, after you do the integration, you get a bunch of these integrals. These integrals are nothing but moments in our context. And now what we have to do is there's a procedure called as moment fitting. And then that essentially gives the quadrature rules for all these background cells. Now, a couple of things to note here is that this quadrature will be different for different FES cells because different regions of the geometry is intersected here, right? So the quadrature that we generate is kind of dependent on the geometry. And one more interesting thing is one of the speakers said, hey, you might run into negative quadratures. That's the case here. We do get negative quadrature values, but so far, it didn't cause any problem, and hope that it stays that way. So yeah, we get this integration rules that are different in every FEA cell. So once you have that, you can effectively separate geometry and FEA. And I don't remember who said this, but someone at Livermore said the role of the geometry is just to compute quadrature points, because once you compute quadrature points, you can throw away the geometry anyway. You don't need the geometry, right? Because like for example, if you have the stiffness matrix, all you need is to integrate the stiffness matrix, and if you want to integrate, you just need quadrature points, right? So so this framework kind of allows users to kind of separate geometry and FEA. They don't have to live together in the same representation. They can live separate lives, and then they can talk to each other through these quadrature rules. So that's a philosophy uh, behind some of the work we do here, and that leads to design kind of a design framework that can separate geometry and material. So in this picture, what I'm showing is the geometry here is represented as a level set grid, as a level set function on a grid, and then the FEA simulation grid is something else. they don't have to be coincident. They can talk to each other through moments. So the FEA simulation, all it needs is moments to compute the integrals. It computes the weak form, minimizes the weak form, and then it gives stress, strain, sensitivities. And the sensitivities go back into this geometry grid. And then the geometry grid will utilize that information, and then it can, update itself depending on the sensitivities. So this decoupled geometry and FEA framework has two, I guess, advantages. You don't really need worry about meshing, and which means you get high level of design freedom. What it means is you can use this framework to highly customize your optimization workflow. You can do topology optimization, you can do field-driven lattice design, you can do functionally graded material design, and it's just in one platform. You can kind of bring in different solvers, different algorithms, and set up a design workflow. So this technology is called Intact Generative. It's available for users, but it uses in-house FEA solver. So most of the users that we have, they usually work on a laptop or a desktop. 16 gigs of RAM, 32 gigs of RAM. And our in-house solver, it's based on shared memory parallelization, OpenMP, and it can comfortably do 3 million, 4 million degrees of freedom. But we are running into situations where people need to solve, tens and millions of degrees of freedom, if not hundreds. And what we have simply doesn't do it. So that's why we are talking. We have a project, DOE project, SBIR phase 1 project, working to bring in MFEM into our ecosystem. We are talking to Sanio and Boyan. They're kind of helping us with this effort. But the goal is to eventually bring in MFEM into our platform and kind of allow access for our users to use MFEM in a mesh-free way. So that's one of the goals of what we are doing. So here from here on, I'll just show some examples on the generative design capabilities that we have. So the first is topology optimization. So this is an interesting geometry. We got it from Onshape. So it's a nightmare to mesh. So because they're very, very small parts, some of them intersect. So they go into each other, there's penetrations, and some are, in a B-rep, some are in triangulated STL format. It's a complicated assembly, to say the least. So the boundary conditions here are, it's fixed on the bottom, and there's some loads applied here. So for us to simulate it, you need to consider the entire geometry to do the simulation, but users just want to optimize one single part in the assembly, right? So our framework allows you to do that because we don't really, we couple geometry and simulation. So the simulation grid is used for the entire part, but the geometry grid is only used in this design domain part. And I'll just play this video so you can see how the topology optimization just updates the design domain here. So in this case, the design variables are the part topology, and the optimization are basically shape sensitivities that we compute. So here, yeah, you don't really go through meshing. You don't have these meshing artifact, and you don't need to do any extra analysis steps for verifying the solution, because you can use the same immersed grid for the optimization and simulation. So you don't need to do any extra steps. So everything is available in one on one platform. The other case is how to do kind of field-driven lattice design. So here in this case, you have a CAD part, you have some loads applied, and you do the simulation, and then you get a sensitivity field. So the sensitivity field essentially is the strain energy distribution. It tells you where the loads are not really intense and where the loads are really intense. What it means is you can remove more material at low strain energy field values. So the blue region here It says you can remove material there. It's safe to remove material there, while the red regions are taking in a lot of loading. So what we can do is we can design a workflow that creates these lattices that follow the sensitivity distribution. So here you can see lattice with low density values, right? You see that the low density values of the hollow regions are populated near the blue areas, where solid regions here are populated at the red regions here. So yeah, in this case, the design variables are these gyro infill parameters, the thickness values, and you can automatically or in an automated way adjust these thickness values depending on simulation. So it's kind of like simulation-driven design. So I showed how you can do topology optimization. I showed how you can do field-driven lattice. Now in this workflow, you can combine them both. So what I'm trying to say here is, so take the geometry, do standard topology optimization, and then you get this topology optimized part, right? Now what you can do is, okay, create a workflow where you have really thick lattices, which means they're almost solid at regions where this topology optimized material has material. And at everywhere else, for example, in this region, the TO part, it doesn't really have anything there, which means you can replace that with really, basic minimum lattices. So for example, here. In this example, so it's a combination of both topology optimized part and field-driven lattices. So you can create all this, intelligent workflows thanks to automated simulation, because you don't have to go through meshing. You don't have to go through pre-processing, right? So you can just put things in a loop, and then you can come up with these cool workflows. Now here's where things get tricky. So fine, you made this, but now ultimately you have to print it, which means as you're printing it, heat gets accumulated, which means you might be running into situations where the residual stresses are really high when you print it, right? So which means you need a really good simulation engine that can capture these small features, which means you will be running into tens or hundreds of million degrees of freedom systems. And our current solver just cannot do it. And this is where we really need MFEM, the MFEM's scalability aspect to help us kind of validate and qualify some of these additive parts. The other thing we can do is, I told how users can bring in different solvers. Like,
you have 3 minutes left.
Oh, okay, sorry. Yeah, so how users can bring in different solvers. But here, in this case, I showed example of how users can bring in different physics as well. So this is flow solver combined with thermal solver. So yeah, that our interoperability platform allows for bringing in different physics as well. So we have commercial deployment. So this is an example. We have a plugin with NTOP. So in this example, we show how users can set up a problem in NTOP using our simulation. And then you can use the simulation results to kind of guide the lattice distribution. And not just that, they can actually see whether or not this design lattice is going to perform as expected here. So after the completion of this SBIR project, we are hoping users of NTOP can have access to MFEM, or at least the best free version of MFEM that we are building through Intact. The other example is we also have an integration with Rhino Grasshopper. So Rhino Grasshopper, it's a CAD platform used mostly by hobbyists. So they don't really understand. I mean, well, we don't really expect them to have like engineering knowledge. They understand forces, they understand stresses, but they don't really understand what quadrature is. So they just want a simple workflow. So this is a NASA challenge bracket problem. Again, it's an assembly, and they just want to design one of these parts in an assembly. So users can very easily set up a topology optimization workflow in Rhino Grasshopper And again, MFEM will be available to all our users after the completion of this project. So they can just, or the mesh-free version of MFEM that we are developing, it will be available to all these users for generative design applications. We also have Intact, which means users can construct automated workflows for machine learning. They can run hundreds of thousands of simulations in batch processing. Just set up a Python code, run it overnight, and then come back, and then you get a bunch of data, and then you can sort through the data, and then you can see what interests you. All right, so my final slide. So we have a lot of R&D projects going on right now. So we are funded by DARPA primarily. So we have an active project where we're trying to optimize both the topology and the process parameters for AM. We also have another parallel DARPA project going on where we want to look at the analysis or simulation of tolerances. So the GD&T tolerances and how that affect simulation. We recently got a grant from America Makes on inspection of additive parts. We have multi-laser PPF simulation project going on with NSF, and we also got some funding from ONR. So as you can see, we clearly need help. So if you're interested in what we are doing, and if you know someone who's interested in what we're doing, please reach out. We are looking for computational engineers to help us in some of these projects. Thank you. I'm happy to answer any questions.
All right, thank you very much. Any questions? Okay, maybe I have a quick question. Is this all this mesh-free stuff? Does it work with higher order finite elements?
Right now we have linear and quadratic. We used to have spline basis functions, but as I said earlier, so the higher your basis functions, the more you have to deal with quadrature. And so we kind of paused on splines, and we are focusing on linear and quadratic shape functions right now.
All right. Okay, any other questions? All right, well, thank you very much for calling in and showing us this. I'm looking forward to see how it progresses.
Thanks for having me.